A fluid has no external shape. It yields to pressure and has the ability to flow. A fluid does not have to be a liquid. It can also be a gas. Before we begin our discussion of fluids, though, we need some basic ideas in mind. The first idea is that of density. We defined it earlier as rho, and we said the density is the mass divided by the volume. Here we have a certain volume. It has mass. And we see what density would be. The second idea we need to look at is pressure. Pressure is the force per unit area. Here we have an area and a force pressing down on it. This generally is expressed in square meters, and the pressure is in newtons, so that a newton per square meter is defined as a Pascal. Now, let's consider this volume. It has a height h, a length here, and a width here. Consider then that the volume is equal to the length times the width times the height. The length times the width is the area. Rewriting then the density, we have it as the mass over the length times the width times the height. If we multiply the rho times the height, we have mass over length, width, height, and height cancels out. Length times width is the area. So rho h is the mass over the area. Now, suppose we have this volume of fluid. What force does it exert down? Well, its force would be mg. We have the mass here. So if we took rho times h times g, then we would have the force per unit area, and we would have the pressure that this area exerts. So, if we were below the surface of some water, we have the water sitting on top of us. And it exerts a pressure of rho times g times the height. Where rho is the density of the fluid, g is the acceleration due to gravity, 9.8 meters per second squared, and h is the height of the water, which in most cases we would call the depth of the water. It's the height of the column above the point we are analyzing. But we do not have to be talking about water or a liquid. We could be talking about a gas. Here we stand on the surface of the earth, and the air above us exerts on us a pressure. On the surface of the earth, that is 14.7 pounds per square inch, which is a number you need to memorize. That is also 101.3 thousand pascals. So we write 101.3 kilopascals. Remember, a pascal is a newton per square meter and is the system's international unit of measure for the pressure. So if you are underwater, you also have not only the pressure of the water, but the pressure of the air. So now if I wanted to talk about the total pressure on you at a depth of h, I would have to say that's the pressure of the atmosphere plus rho times g, rho being the density of the water or the fluid, g the acceleration due to gravity, and h would be the height of that column, or in this case it's the depth. Next we study Pascal's principle. developed by Blaise Pascal, who was a contemporary of Isaac Newton, only about 15 years older. And Pascal died at the early age of 39, but contributed a great deal to science. He considered that if you had a large vessel of water, think of a swimming pool, and you were down at a certain depth, which we'll call H, the pressure on you would be the same anywhere in that pool if you stayed at that depth, because it depended upon the atmospheric pressure pushing down and the pressure of water, as we saw before, where the total pressure is equal to the pressure of the atmosphere plus rho GH. So Pascal then divided up the water, let's say your pool, into two sections like this. And he concluded that if you were over here, since the height of the water is the same here as the same here, that the pressures are the same because they're connected by the reservoir in between. So it does not matter what the shape of the water is. Here could be the water, and here is an underground cliff, let's say, overhanging the water. And if you swim down here, the pressure at this point is the same thing as the pressure at this point, because the fluid itself evenly distributes the pressure all over. And so if you're at this height, or depth, height H, height of column of water above you, the pressure will be the same no matter where you are. No matter what is over you, the pressure is transmitted by the fluid, and that was Pascal's idea. So, as long as you are at some depth and have a height of column of water above you, the pressure at 1 is equal to the pressure at 2. But the pressure is the force per unit area. So the force at 1 over the area at 1 is equal to the force at 2 over the area at 2. Now let's design the reservoir a little differently. Let's make this pipe quite a bit smaller than this pipe and connect them by a fluid in between, so that this is area 1, much smaller than area 2. But Pascal's principle says that the fluid in between them will transmit and make the pressure the same. So I have the force at 1 over the area at 1 is equal to the force at 2 over the area 2. So let's put a force on top of area 1. What is the force then pushing up at area 2? Now, solving for force 2, we have force 2 is equal to A2 over A1 times force 1. So let's suppose that A2 is 100 square meters, A1 is 10 square meters, and force 1 is 500 newtons. So we will push down force 1 with a force of 500 newtons. And we will put some kind of little block over here on top of the fluid. What force does the fluid push up on that block? Now I have F2 is equal to 100 square meters over 10 square meters times F1, which is 500 newtons. The square meters cancel out, and we are left with 5,000 newtons. What? Yes, it says that if we push down with 500 newtons and the areas are 10 to 1, then the forces will be 10 to 1. This is exactly how a hydraulic lift works. We could put a car right here, and with a relatively small force, we could push on this end, and now we generate a huge force at F2 from a much smaller force at F1. And this is the principle behind all hydraulic systems, that they allow a small force to lift a very large force at the other end. Or likewise, we might want to push on F2 with a big force and we would move the fluid in here a much longer distance.